dense. Soon it will hide the snowball in the middle. The cloud grows. The sunlight is reflected in the dust and the comet gets brighter and brighter. We call this cloud the comet's coma. As the comet comes closer to the sun, the intense sunlight pushes the molecules and the dust in the direction away from the sun. The sunlight heats the coma and the temperature rises all the time. The sun's ultraviolet light breaks down the molecules in the coma. Some of the molecules and atoms are electrically charged. They interact with the so-called solar wind, that is, fast particles emitted by the sun. A long, straight ion tail is then formed, which points away from the sun. When the ice and snow evaporate from the nucleus, the dust grains fall out. As the comet moves, they are left behind and form a broad, curved dust tail. It shines because of reflected sunlight. But the ion tail glows by itself because its molecules and atoms are very energetic. Here is the first ion tail of Comet Halley. There were several such tails at the same time. We are now about to see one of the most remarkable sequences ever obtained of a comet's ion tail. A very sensitive wide-field camera was installed at La Silla in February 1986, just after Comet Halley had passed the point closest to the Sun. For 2.5 months, many exposures were made every night of Comet Halley's ion tail. More than 800 pictures were taken to document the changes in unsurpassed detail. The camera registered the light from carbon monoxide ions in the tail. The time of exposure is shown in the lower right-hand corner. This project was directed by ESO astronomer Holger Pedersen, who also computer-processed the pictures for scientific study. Here we go. We can see how the tail changes, and the outward motion is very obvious. If we watch carefully, we can also see big blobs in the tail that sometimes move outwards. Sometimes the tail bends and twists. This is when Halley passes through regions in interplanetary space where the magnetic field is disturbed. This field interacts with the electrically charged ions in the tail. Some of the images are overexposed because the moon interfered in the second half of April. We have now seen the development of Halley's ion tail over 2.5 months in just 1 minute. We now repeat the entire sequence at half the speed for greater clarity. The spacecraft Giotto passed Halley on March the 14th. Here we have another disturbance in the tail. The jumping bright spots have nothing to do with Halley, however. They're reflections in the camera from bright stars. Now, a blob in the tail is moving outwards. It's a concentration of carbon monoxide ions, which is pushed away by action of the energetic particles in the solar wind and the associated magnetic field. We see a lot of activity in early April. Large parts of the ion tail are ripped off. By studying the motion, it's possible to measure the strength and direction of the magnetic field in interplanetary space. On April the 11th, Comet Halley was closest to the Earth. Some days later, Halley passes a magnetic boundary in space. There, the direction of the magnetic field reverses. This is recorded by the fast motion in the tail. It bends and twists and also shifts sideways. On May the 1st, a condensation was observed in the tail for the last time. In early May, the brightness of Comet Halley decreases. The orbital motion carries it towards the Milky Way band, and there are noticeably more stars in the field. The ion tail fades until it's hardly visible anymore. This is the control room, where the images were recorded. The film was made on the 4th of March, when a big condensation was discovered in the tail just one day before the first of a total of 5 spacecraft flew past Halley. The images we have just seen are of great scientific value for the study of Halley's tail and the interplanetary magnetic field. That is particularly